This is ICP Chapter 1-3 Measurement. This topic is covered on pages 14 through 21. Scientific notation is a way of writing numbers that makes very large or very small numbers easier to work with. The expression of the number has three parts: the coefficient, the base, which is always 10, and an exponent. The coefficient must always be between 1 and 10. This diagram shows how to convert to and from scientific notation. Here in step 1, move the decimal to make a number between 1 and 10. And so for this particular number, 240,000, the correct placement of the decimal is between the 2 and the 4. If you place the decimal here, the coefficient is less than 1, which is not in the range that we want. And if you put the decimal here, that makes it 24, which is greater than 10. So you want to make sure you place the decimal here so that the coefficient will be between 1 and 10. Step 2 is to count how many places the decimal point moved. Originally the decimal point was here. Although we don't write it, it's invisible, but on whole numbers it would be here after the last 0. And when you count the number of steps, it winds up being 1, 2, 3, 4, 5. So to move the decimal from where it was actually located to where it's going to be located in the scientific notation coefficient was 5 decimal places. The last step is to write the number without all the zeros, because it turns out they're not significant, which is a topic we'll discuss later. So we wind up with 2.4, the multiplication symbol, the base of 10, and then because we moved the decimal 5 places, the exponent is positive 5. Now it's also possible to write numbers smaller than 1 using this same scientific notation. So here we're writing 0.000048, and the technique is very similar. Again, you're going to move the decimal so that the coefficient is going to be a number between 1 and 10. In this case, it's between the 4 and the 8, and you wind up with a 4.8. You lose all the zeros, and when you count the number of spaces it took to move the decimal from where it was to where it winds up, it's 6. 1, 2, 3, 4, 5, 6. Now, because this number was smaller than 1, and also because you moved the decimal to the right, this becomes or is written as a negative power of 10, or a negative exponent. So when you're reading scientific notation, if the exponent is positive, that means you've got a number bigger than 1, and when it's negative, it means that the number is less than 1. One other skill to be able to do is to change from scientific notation to standard form. In this case, we start with a number in scientific notation, 5.3 times 10 to the 7th, and we do the process in reverse. Step 2, we're moving the decimal 7 places because the exponent is 7. Now, the instructions emphasize the direction because we're moving the decimal point to the right, or we move the decimal point to the right because it is a positive exponent. I prefer to think of it in terms of, if I see a positive exponent, I know that my resulting number is going to be bigger than 1. And so I move the decimal this way to make the resulting number bigger than 1. In this case, it moves 7 places from where it was to where it is in standard notation. And the final form then in standard form is 53 million instead of 5.3 times 10 to the 7. One other skill that is used with exponents is multiplying and dividing numbers that are in exponential form. Now, if you're lucky enough to have a calculator that will do this for you, this is a bit of an archaic skill, but it's always nice to know how to be able to do this, not exactly by hand. It still helps to have a calculator to do some of the basic math, but in any case, when you're multiplying numbers in exponential form, you have to sort of break the numbers up into the coefficient and the exponent, and you treat them separately. You deal with them completely separately. So in this case, this is the coefficient of the first number and this is the coefficient of the second number, and you multiply them together as you would any other number. So it's 2.5 times 5, which winds up being 12.5. And this is going to be the coefficient of the new number. We see that winding up down here. The way that you deal with exponents and multiplying is you add the exponents. So the exponent of the new number will be 17 plus 14, which gives you 31. So it's 12.5 times 10 to the 31st power. Now the problem is this coefficient is not in standard form. 12.5 is bigger than 10, so we actually need to, as the final step, move the decimal one place over to put it between 1 and 2, so that this number now is between 1 and 10. Now the thing is, as you move the decimal, it also changes the power, or the exponent. So it goes from 10 to the 31st power to 10 to the 32nd power to make up for the movement, or to correlate with the movement of this decimal from where it was to here. Division is similar in the fact that you have to divide up the number into the coefficient and the exponent. And once again, you divide the coefficients as you would regularly. You could just type it right into your calculator, 2.5 divided by 5, and that comes out to be 1/2, or 0.5. Now, dealing with the exponents, in this case, instead of adding them together as you did in multiplication, the operation is actually subtraction. So it's this exponent minus this exponent, which winds up being positive 3. So the initial outcome of this calculation is 0.5 times 10 to the third. But again, this coefficient is not in standard form. It's got to be between 1 and 10. And so to do that, you have to move the decimal over, but when you move the decimal, it changes the power of 10 from 10 to the third to 10 to the second. Historically, the metric system originated in France in the 1600s. The original, actually current name in French and in most other countries, is the International System of Units. After considerable development and change, it was officially adopted by France in 1795. It's a decimal system, which means it's based on multiples of 10. And today in the United States, in 2015, is the only industrialized nation not to have completely converted to the metric system. There's a common sentiment about the metric system in this country. The metric system is made up of a number of base units. These are the main base units. The ones we'll be using in class most often are mass, length, time, temperature, and when we get to chemistry, we will be using the concept of the mole. There are also numerous what are called derived units, which is what you get when you multiply or divide base units while solving for different formulas. I'm not going to focus a lot on doing conversions between metric and English units, but just so that you have an idea of real-world values, a paper clip has a mass of about 1 gram. A meter is slightly longer than a yard. It's about 39.5 inches. 2-liter bottle of soda is, well, 2 liters. And temperature-wise, in the Celsius system, water freezes at 0 and boils at 100 degrees Celsius. In addition to the base units, the metric system uses prefixes to allow for naming and describing units larger and smaller than the base unit. Here are the metric prefixes that are closest to the base unit, the named ones. I won't go through the entire list. The way you use metric prefixes is you say or write them before the base unit, which then changes the value of the unit to be some multiple or some fraction of the base unit. So a kilometer, because the prefix kilo means 1,000 times bigger than the base unit, a kilometer is 1,000 meters. You can also have kiloliters, kilograms. All of the prefixes work with all of the base units. Here are some common equivalents of the sort that we might see in a ICP lab. Now, mathematically, there are a couple different ways to convert from one metric unit to another. In fact, this is one of the strengths of the metric system, ease of conversion. You don't have to memorize that there are 1,760 yards in a mile. Instead, everything is based on powers of 10. And so, as we discussed in class today, all the base units would fit into the center of this number line. And then as we converted, say, to deca or hecta or kilo units, you would slide the decimal from its previous position 1, 2, or 3 spots to the left. You move it the same number of spaces and the same direction. Same thing if you're converting down to smaller units. A tenth, a hundredth, a thousandth of the base unit, you're sliding the decimal 1, 2, 3 places to the right. Precision and accuracy. They are sometimes used interchangeably, but they actually mean different things. Precision is a gauge of how exact a measurement is. Usually this is limited by the instrument that you're using to make the measurements, and some instruments are more precise than others. And to go along with the concept of precision is the concept of significant figures, which is all the digits or numbers that are known in a measurement, known for sure. And the precision of a calculated answer is limited by the least precise measurement used in the calculation. So here we've got measurements taken by 2 different instruments. A ruler or a meter stick is accurate to 1/100th of a centimeter, which is the limit to its precision. And so there are 1, 2, 3 numbers that you know for sure about that measurement. On the other hand, an analytical balance, being a rather sensitive and expensive piece of equipment, has 6 significant figures, all the way out to 10,000ths of a gram. So this is a more precise measurement, although it's not necessarily more accurate. Accuracy is a measure or a gauge of how close a measurement is to the actual value. It's not the same as precision. So here we've got some diagrams showing groupings of data points or target shots that have both high precision and accuracy, high precision and low accuracy, high accuracy and low precision, and neither. Measuring temperature. The base unit in the metric system is the degree Kelvin, although it's not used fairly often, even in countries that do use the metric system. The Celsius system is much more commonly used. You would add 273 degrees, and these formulas show how to convert from Fahrenheit